Today we will discuss about data dependency, the hidden bottlenecks in a code. Most people think computer performance is still about the clock speed, like a higher gigahertz means faster programs. But that's not a full story. What actually matters is how smoothly data flows inside the processor. When we write a code, it looks like a simple instruction step 1, step 2, step 3. But inside the CPU, there are invisible forces control how fast those steps can actually execute. One of the most important of these forces is called data dependency. These dependencies acts like a hidden bottlenecks. So what exactly is data dependency? In simple terms, instructions in a program are not independent. Most instructions depend on the result of previous one. It's like a relay race. One runner must pass the baton before the next can continue. Now, this is not just about the speed, it's about correctness. If we try to execute instruction too early or out of order, we might get the wrong result. That's why data dependency management is critical. In modern processor, we use something called pipelining, where multiple instructions are processed at the same time. While the improves speed, it also introduces conflicts called data hazards. There are three main types: R- raw, read after write. This is the most common type. An instruction tries to read data before it has been written. WAR, write after read. A later instruction tries to overridden data before the earlier instruction finish reading it. WAW, write after write. Two instructions try to write at the same location and the order matters. The true dependency. Let's focus on the most important one, RAW or read after write. This is called a true dependency because there is no way to avoid it. Imagine this: instruction 1 writes a value into register. Instruction 2 needs that values. Instruction 2 literally cannot process until instruction 1 is finished. A simple analogy: you can't read the last chapter of a book if the author is still writing it. Because of this, the CPU may introduce a stall, meaning it pauses a few cycles. During this time, the processor is basically waiting, which reduce performance. That's why row dependency are a major bottleneck. Now let's look at a war, the anti-dependency. This is called an anti-dependency because it's not a real data flow issue. It's more about a resource conflict. Here is the problem: an instruction need to read a value, but a later instruction tries to override that value too soon. If we reorder instruction carelessly, we might lose the correct data. But the good news is this problem can be solved. Two common techniques are instruction reading. The compiler arranges instruction to avoid conflict. Register renaming. The processor use different register internally, like giving a new name to avoid overwriting. This allow execution to continue smoothly without waiting. So overall, data dependencies are one of the key reasons why performance is not just about hardware speed. Understanding them helps us see how programs actually behave inside.
And let's start with our next slide, which is WAW, the output dependency. So I will begin with WAW dependency, also known as write after write. WAW occurs when two instructions write to the same register or memory location, and the final result depends on the order of execution. For example, if two instructions store values into the same memory address, the value written by the last instruction will be the final result. So, here, maintaining the correct order is very important to preserve program correctness. A simple way to understand this is: imagine two painters painting the same wall. The final color emphasizes on who paints last. The final color depends on who paints last. Now that we understand WAW, let's see how these dependencies actually affect processor execution. Now, Now, in modern processor, instructions are executed using a pipeline typically consisting of five stages. Instruction fetch, decode, execute, memory, and write back. When dependencies like WAW or especially RAW occurs, the processor may not be able to execute instructions smoothly. This leads to pipeline stalls where some stages have to wait, reducing efficiency. So instead of continuous execution, we get delays or bubbles in the pipelines. Now, when we talk about what are the causes of dependency, this stalls directly increases execution time. For example, without any optimization, more cycles are needed due to waiting. This reduces overall performance. The main reason is that dependent instruction cannot proceed until the previous ones are complete. Now, if we talk about optimization technique, to overcome these issues, processors and compilers use several techniques just like forwarding, instruction reordering, and register renaming. In forwarding, data is directly passed from one stage to another without waiting for write back. Instruction reordering, the compiler rearranges the recording instructions so that the independent instructions are executed in between dependent ones. And at last, the register remaining, in which different registers are used to eliminate failed dependencies like WAW, false dependencies like WAW and WAR, allowing better parallel execution. Now, for performance improvement, with these optimizations, the number of cycle reduces. For example, from around 10 to 7 cycles. This result in nearly 30% performance improvement, which is very significant in high-speed processor. So to conclude, WW dependencies highlight the importance of execution orders and along with the other hazards, it play a major role in determining pipeline efficiency and processor performance. Modern system relies on smart techniques like forwarding and register remaining to handle the challenges effectively. Thank you.